Good morning, everyone. My name is Kangli. Today, we'll introduce our work AnyPcc, compressing any point cloud with a single universal model. This work is done from Peking University and Pengcheng Laboratory. Point clouds are becoming increasingly important in many 3D applications, such as autonomous driving AR and VR, digital humans, and 3D reconstruction. However, raw point cloud data is extremely large. For example, RGB point clouds, LiDAR scans, and 3D Gaussian splatting point clouds all require very high bandwidth if transmitted without efficient compression. This creates an urgent need for powerful 3D data compression algorithms, especially algorithms that can support different data formats, densities, and application scenarios. The key insight of this work is that real-world point clouds are highly diverse. They may come from LiDAR scans, indoor scans, human point clouds, or reconstructed point maps such as 3D-GS and VGGT. These data types have very different spatial distributions, resolutions, and densities. So the central question we ask is, can we use a single model to efficiently compress all these heterogeneous point clouds? Existing approaches still have clear limitations. First, most learning-based compression methods are trained and tested on similar data distributions. They work well on in distribution data, but their performance often drops significantly when facing out of distribution point clouds. For example, a model trained on sparse point clouds may not generalize well to dense point clouds. Second, implicit-based compression methods transform point cloud compression into model compression. These methods usually have stronger generalization ability, but they often require a long encoding time because they need to overfit a model to each individual point cloud. Therefore, we need a method that is universal, robust, and efficient. To achieve this goal, we identify three key challenges. The first challenge is how to use one model for heterogeneous point clouds. The second is how to maintain robustness when the test data is out of distribution. The third is how to speed up encoding for implicit compression. To address these challenges, we propose AnyPcc, a unified point cloud geometry compression solution. It combines a powerful universal context model, or UCM, with instance adaptive fine-tuning, or IAFT. The AnyPcc framework has two main components. First, the universal context model introduces channel spatial grouping. This design helps the model handle point clouds with different densities and spatial structures, improving its generalization ability across diverse data. Second, instance adaptive fine-tuning performs online fine-tuning during encoding. This allows the model to quickly adapt to each out of distribution sample. After adaptation, the bit stream transmits both the compressed point cloud and the adapted weights. In this way, AnyPcc combines the generalization of implicit methods with much faster and more adaptive encoding. To conclude, AnyPcc provides a unified and adaptive solution for compressing heterogeneous point clouds with a single model. Thank you for listening. Experimental results show that AnyPcc achieves state-of-the-art performance on both lossy and lossless compression. More importantly, it demonstrates strong generalization across diverse datasets, including LiDAR scans, indoor scans, human point clouds, and reconstructed point maps. The online fine-tuning curves also show that IAFT can adapt efficiently during encoding. For future work, we are interested in two directions. The first is exploring scaling laws for compression models. The second is using self-supervised learning and better data curation to further improve universal point cloud compression.